We'll record just in case I say something useful. Today, we're going to hit our trigonometric substitution finale. We're going to do just a couple of examples of trigonometric substitution problems where we go through the entire process. So we've been looking at it in parts: phase one, the substitution; phase two, the integration part; and phase three, the unsubstitution parts, where we build a little triangle. So we don't write ridiculous things like cosine of sine inverse of x over 3 and stuff like that. I want to start off with a problem that we already know. Anytime we're learning a new process, and the process should be backwards compatible, we should see that process being backwards compatible. When the PS6 comes out, we should be able to play all of our PS5 games on it. So we're going to apply the process to an integral that we already know, because the point of the process is not to find the antiderivative, but to understand how things are put together. So let's take a look at an example where we already know. So in this problem, we have a 9 plus x squared. We know that this is going to end up being 1/3 arctangent of x over 3. We know that that's going to happen. We know where the x over 3 is going to come from because we've studied the process. We're about to write x equals 3 tangent theta. So theta will be arctangent of x over 3. So we can see all this stuff. And we're going to see where that 1/3 comes from. That's present in the arctangent, but not in arcsine. So we're going to set up our substitution. If since it's 9 plus x squared, we have the form a squared plus x squared. This quadratic form suggests this substitution, the tangent case of trigonometric substitution. If x is 3 tangent theta, then dx is 3 secant squared theta d theta. Once we have these parts, I shouldn't call them parts, we can make our substitutions. The dx will be 3 secant squared theta, and in the denominator we'll have 9 plus 3 tangent theta squared. Forgot the d theta. After we make our substitution, this is when the Pythagorean identity shows up and two terms become one term. Wherever we made that substitution, in the 9 plus x squared, that's where we suck down into one term. All the normal stuff happens. We know that this is going to end up being a 9 secant squared theta. We're going to write it down because we're practicing. So this is 9 plus 9 tangent squared theta. We can take out the 9, and that reveals the 1 plus tangent squared theta. And so the denominator is 9 secant squared theta. So this next step is the entire point of doing the trigonometric substitution. That quadratic form in 2 terms gets pulled into 1 term, the power of a trig function. Now, in this case, something cool happens. We spent a lot of time focusing on the integration. That was product powers of trig functions. That's not substitution. But in this case, everything cancels out. Oh, I should have a 9 secant squared. Pardon me. I was looking too far ahead. So the secant squareds cancel out, and we have 3/9. So we have the integral of 1/3 d theta. There is our theta integral. So when we integrate our theta integral to find our theta antiderivative, we just get 1/3 theta plus c. So here we are at the capital G of theta, our theta antiderivative. So in this case, the integration was not a product of powers of trig functions. That was not substitution. This was the easier one. Now I need to take the x equals 3 tangent theta, and I need to figure out what theta is. So if x is equal to 3 tangent theta, then tangent theta is equal to x over 3. And so theta is arctangent of x over 3. Just like we suspected. The integral of 1 over 9 plus x squared is going to be a third times the tangent inverse of x over 3. When we learn a process, we got to make sure that it still works on things that we already know. We want to make sure that it's backwards compatible. Here was an example of the entire process. We started with our integral, our x integral had that quadratic form. We use a trigonometric substitution of the tangent case. Once we made our substitution, the Pythagorean identity took two terms into one term. Our quadratic form dropped down into a power of a trig function. Then we arrived at our theta integral. We integrated it, and then we unsubstituted. In this case, we didn't need to do the triangle bit because all we needed was theta. When we start going through the process and paying attention to what we're doing, we can see why our integral of 1 over the 9 plus x squared is 1/3 arctangent of x over 3. But in our integral of 1 over the square root of 9 minus x squared, we can see that we're not going to have that 1/3. It's just going to be arcsine of x over 3 because of that square root. That square root is going to drop the 9 and the 9 from that secant part from our Pythagorean identity. It's going to drop that 9 down to a 3, and it's going to cancel the 3 that shows up from the dx. So let's see that happen. We see this, our x integral has a quadratic form in it, and that makes us think about trigonometric substitution. Then we get all happy because that's our favorite. And it's the sine case because it's a squared minus x squared. So x will be 3 sine theta. Dx will be 3 cosine theta d theta. We're going to make our substitution. The dx will be 3 cosine theta to theta. In the denominator, we have the square root of 9 minus x squared. In this case, x is going to be 3 sine theta. Then the trigonometric substitution thing happens. Now we're going to do the thing. 2 terms become 1 term. 9 minus 3 sine, the 9 minus the square of the product of 3 and the sine of theta is going to become 9 cosine squared theta. Let's square our sine term. Factor out the 9. And then replace 1 minus sine squared with cosine squared. The usual. Now, in this case, we have the square root of 9 cosine squared theta. We only have a cosine in top, but we only gonna have a cosine in the bottom, and they're both gonna cancel out. So the square root of 9 cosine squared theta will simplify to just 3 cosine theta. So our integral is just going to be 1 d theta. Now we can see why our arcsine does not have the coefficient 1/3, but our arctangent does have the coefficient of 1/3. This is easy to integrate. We end up with theta plus c. Now we're at our theta antiderivative. We need to go to our x antiderivative by doing the unsubstitution. If x is 3 sine theta, then sine theta is x over 3, and theta is sine inverse of x over 3. Once again, we didn't need to do the triangle thing to figure out what cosine was because we didn't end up with cosine. Is everybody okay? A lot of times we start doing these trigonometric substitutions when we have radicals, specifically square roots, in our functions. Mostly because when you have the square root of these quadratic forms, I can't simplify the square roots of 9 minus x squared. I can't distribute the exponent over a sum. But if I could take that sum and write it as just one term, if I can take that sum and transform it into a product, I can apply the radical, the exponent, to each of the factors. So one of the important things that's going on here, I don't know if important is the right word. That's the word that I usually use. But anyway, one of the important things to recognize here is that I can't do this square root of 9 minus x squared. Exponents do not distribute over sums, but exponents do distribute over products. That's an important thing to recognize here if we take this all the way back to arithmetic. So here we are noting that exponents do not distribute over sums. But if we can do our trigonometric substitution bit and combine those two terms into one term, then we're over here. Exponents distribute over products. There is a distributive property for exponents over products, but not over sums. And it's important that we recognize that that radical is a 1/2 exponent. So exponents distribute over products. If I have x, y to the n, that's x to the n times y to the n. But x plus y to the n is not x to the n plus y to the n. That's why we can't simplify the square root of 9 minus x squared to 3 minus x. Exponents do not distribute over sums. multiplication distributes over a sum. That's the typical distributive property that we see. Having shown you A parentheses B plus C close parentheses equals AB plus AC, we ruined parentheses for you. That is the source of all those mistakes where you just distribute stuff when you're not even multiplying. Because we say this is the distributive property, we show you what it looks like. We give you its visual form rather than tell you what is going on. We keep trying to we were trying to classify things with a visual form, but not explaining what's going on. And so you just see the form instead of the function. That makes sense? This is an important thing to notice. How your math education has betrayed you. Multiplication distributes over addition. Multiplication distributes over products. The problem is, instead of phrasing it this way, we just show you this. And then call it the distributive property. This is where we fucked up. And so every time you see something in front of parentheses with an addition, you just distribute it. Because you're like, oh, distributive property. A parentheses B plus C equals ab plus act. Then you come along, and then you, of course, your teachers are dicks about it. And you're like, and they're like, oh, natural log of X plus Y. And you're like, oh shit, I've seen this before. I'll distribute natural log of X plus natural log of Y. And then your teacher's like, oh no. Your teacher's all mad at you. And you're like, oh, what? But the distributive property. And they're like, oh, why? And then you say, why not this? The problem is your teacher doesn't know. They're like, well, because no. They're like, well, son of a bitch, it's because natural log is not multiplication. We're not multiplying natural log times anything. It's natural log of this shit. You know what I mean? Don't get mad at your teacher. They didn't know. Don't get mad at people for being the way that they're raised. Don't be mad at people for being the way that we raised them. Anyway, that's the going all the way back to arithmetic. This is why we do this stupid trig substitution stuff. I don't know why I spend so much freaking time on it, but this is why it has to happen. Usually it's because we have a square root of something squared that's in an addition. And so we're like, oh, we don't like that. I want this square root to be applied to something that's a product so I can distribute this square root and maybe simplify my process. How's everybody okay? This is way more fucking detail than anybody needs ever in this, but the brief that I was given for this was like, oh, teach students about that. And I'm like, oh, got it. Then I show them what I'm doing. They're like, oh, no, not like that. Just make them do stuff. We want factory workers. I'm like, oh, you didn't spec factory workers. You said educate. I like to do variations. What case of trigonometric substitution should we use on this integral? Be careful, that was a trick question. I am deliberately laying an obvious trap for you to fall into. Listen carefully how I phrase the question. What case of trigonometric substitution should we use on this integral? 1 over 9 minus x squared. Why are we not going to use sine case of trigonometric substitution? Obviously, it's a squared minus x squared. We should use a sine case of trigonometric substitution, right? This is a hard question because we spent all fucking week on trigonometric substitution. I programmed you to think and see in trigonometric substitution. But notice that I've got 1 over 9 minus x squared. What do we notice about 9 minus x squared without that radical sitting on top of it? What we want to notice is that this denominator is factorable. And so we should partial fraction decomposition. Now we'd need to go and figure out what A and B are. The 9 minus x squared is factorable. The reason we didn't do it on a 9 plus x squared is because 9 plus x squared is not factorable. That's not, I couldn't do partial fraction decomposition anymore on that one. So. Moreover, we've got the big chunk of what we want. Now this raises a question. What happens if we use trigonometric substitution? That's a great question. You should find out. I skipped the stuff that we know is going to happen. 9 minus x squared under the trig substitution is going to become 9 cosine squared theta. So notice what we get here. We get a 1/3. And then the integral of 1 over cosine. But what is 1 over cosine? Secant. And what's the integral of 1 over secant? Or sorry, what's the integral of secant? Natural log of absolute value of secant theta plus tangent theta. Obviously, right? There's our theta integral. At least now we can see what A and B are going to be. But now we have to undo our theta integral. Ugh, this is just nothing but work. So if x is equal to 3 sine theta, yeah, then sine theta is x over 3. I don't need theta, so I'm not going to bother with theta, but we are going to need cosine and tangent and secant. So we're going to draw our little triangle. We're still drawing it because we're still new at this, but we know what's going to happen. We have opposite and hypotenuse, and so adjacent is square root of 9 minus x squared. The third side of the triangle is always the thing that got you into this situation in the first place. So we can say cosine of theta is adjacent over hypotenuse. Oh, I don't need cosine, do I? But I do need secant of theta. And we will also need a tangent of theta is opposite over adjacent. I'm not going to fit it here. That was a little ambitious. So we have to get back to our x integral. Secant is going to be 3 over not square root of 9 minus x squared. And tangent is x over 9 minus x squared. Sorry, square root of 9 minus x squared. Now, at this point, we're looking at this and say, dude, this does not look like what we had. But at least now we can see that A and B are both going to be 1/3. What we can do is combine these terms. They have the same denominator, so I can just add them up. But then we got to start wondering, how does this get to a 3 minus x and a 3 plus x? So at this point, it's help us, algebra. You're our only hope. Questions? It's not that we can't do trigonometric substitution in this scenario. It's just that there is a shorter thing that we can do. I know I didn't solve for A and B in our partial fraction decomposition, but still, that's just doing some algebra, putting these together to figure out what A and B are. Or we can combine forces with trigonometric substitution, not go all this way and find out that the coefficients are going to be 1/3. So maybe that's helpful. How's everybody okay? Now, the other thing I want to remind you of is, remember, I'm not going to put on some quiz or test or final exam the integral of 1/9 minus x squared, because we've already done it. It'd be crazy to ask you that question now. We've done the problem. I also wouldn't just switch things up in that clever way. So how about dx over 25 minus x squared? Ooh, because that doesn't do shit. If you can't tell the difference, that 1/9 minus x squared is the same as 1/25 minus x squared at this point in your mathematical career, I do not know how you got to this point in your mathematical career. You don't get to be fooled by some prime number shit. Or am I going to just turn the 3's into 5's? And then let her rip. Like, if you're like, oh, whoa, that's really thrown me off, then you're further behind than we thought. If that is an issue, you need to let me know, because we got to fix that. But the reason that I go into all these details on problems that you're not going to have to deal with any kind of practical sense is so that we can build that recognition. So that if I suddenly drop this, if I give you the integral of 1/25 minus x squared, you are not confused. In fact, you don't even write stuff down. It's just going to be a 1/5 natural log of 5 minus x plus 1/5 natural log of 5 plus x. I think one of those ends up being minus. Doesn't matter. But I can't remember which one it is. That's why I left it in A and B. But you're not going to be fooled by that. You know what's going to be happening. Does that make sense? That's the thing that I care about the most. This one, no, this one is minus. This one is plus, because I'm going to do natural log of 3 plus x minus the natural log of the square root of 9 minus x squared. I think that's the way it goes. That doesn't matter. The reason that I go into all these details about these problems, straightforward problems, is so that we start seeing the patterns in things. We want to see the patterns so we don't have to write down all this math all the time. The point of the math class is to avoid writing down all this math all the time. Now, this does not invalidate when your teachers are like, oh, show your calculations, because they want you to see you writing this down all the time. Their professional opinion says, I want to make sure that they are writing this down, because it's going to be very easy for students to talk themselves into not writing shit down and saying, oh, yeah, I know what's supposed to happen. I'm just going to look it up on Wolfram Alpha because I know all this. Because we're not very good at studying. We look at a page of notes and we say, do I know how to do this problem? And we tell ourselves, yeah, you know how to do that problem. You're like, oh, yeah, I agree. And then just go on to the next problem. You know what I mean? That's shitty studying when you just read over your notes. If you're in a math class and you don't have pencil and paper, then you ain't studying. If you ain't writing, you ain't studying. This is a skill that you need to practice. Now they're like thinking, I am going to practice basketball and then turn on an NBA game. Just watch it. That's not how that shit works. You want to get better at the skill, you have to do the skill. Combinations of things. So here we have done something significant. I'm like, oh, 1 over the square root of 9 and the x squared. You're like, well, is it minus? Because we've done that one. No, it's plus. So it's like, son of a. I didn't do this one previously, did I? No, I was just thinking about it earlier in my office, and that's why I thought I did this problem. So this one does fit that category. We've got the square roots of this stuff that's being squared. We've got the square root of this quadratic stuff. And there's no partial fraction decomposition to help us because of the stupid square root. So we're like, oh, damn it, Leach, why do you have to give us some trigonometric substitution? Or you could be like, oh, yay, we get to do trigonometric substitution. This is where we're going to practice knowing what's supposed to happen. We know that the 9 plus x squared will be a 9 plus 9 tangent squared theta. And so that's supposed to be a 9 secant squared theta. I'm not sure that we're ready to start skipping steps, but it's okay. You're being watched, so it's important to recognize remember what the point of the process is so that you can start predicting where the process is going to go. But also remember that we just skipped some steps here. So if something doesn't work at the end of our problem, then we know the first place to look that something has gone wrong. We expected a thing to happen. If our problem didn't work out, go back to where we expected things to happen and think and check. Did this work out right? The square root of 9 secant squared, I'm going to simplify this to 3 secant theta, secant theta. The 3's cancel and we're integrating a secant theta. The integral of secant theta is the natural log of absolute secant theta plus tangent theta plus c. And now we've come to the point of this exercise. In the previous problem, we also had a natural log of secant theta plus tangent theta, but those thetas are different than these new thetas. I'm not going to use 3 over square root of 9 minus x squared for our secant theta because that's not secant theta here. This all comes from x equals 3 tangent theta. So tangent theta is x over 3. So this tangent of theta is going to be an x over 3, and then we'll need a triangle with an opposite and an adjacent. To get our secant theta. So secant theta is hypotenuse over adjacent. So our x antiderivative is going to look a lot different. So natural log of secant plus tangent. If I did happen to put this on a quiz and you gave me this response, perfectly acceptable. If you really want to look cool, you'll drop the denominators of 3 because they're constants. I just realized yesterday I never explained where the threes went. I should explain where the threes went. If I explain where the threes went, like right now, since it's fresh in our minds and we've just seen it happen, I should explain where the threes went so that you'll understand why you can get rid of them, so that you could be the cool dude that doesn't write his constant denominators and his natural log sums. I mean, it's perfectly happy to leave the threes, but if you want to be cool. But I should explain it right now. That'll clear a lot of things up and kind of help a lot with the previous problem. Save yourself a lot of algebraic exploration. So why don't I explain where these threes went so that you'll really get a more solid basis for algebra to really understand how things go. So here it is. Ah, dang it. Look at the time. That's going to do it for today. That's going to do it for this week. I guess the weekend cliffhanger is where do threes go? All right, that's it for today. That's it for this week. I'll see y'all on a Monday. Everybody have a good weekend. Thanks for playing. I'll be in my office tomorrow and on Zoom if you have questions.